I know, nevertheless, so go ahead, Jerry.
Thank you, thank you. I'm going to be talking this morning about the Euclid telescope, which the European Space Agency has sent out to settle a controversy as to really understanding in a quantitative way how the universe has evolved. That's the text of the talk. And parts of it will be hard for some to understand, but stick with it and just have an appreciation for a group of people who are willing to work like the devil to just refuse to not bring everything together in a nice, tidy package. Because there is a discrepancy right now in two ways of determining a very important and particular number. I was so struck by the drama of what I'm showing you on this slide. It's a fraction of the sky, about a 20th of the sky, as it was taken by the Sloan Digital Sky Search, a thing that's been going on. It's limited because it's Earth-based, and so the furthest out that it can see is just about 6,000 billion light years away. And this represents a group of stars that are a group of galaxies, I should say. They're not stars. Each one of these things is just like our Milky Way. So it's made up of billions of stars. And that's a 20th of the sky. In the horizontal direction, you're looking at something like 6 billion years. In the vertical direction, it's 4.5 billion years. And the thickness of what you're looking at is about 500 million years worth of light. And it is trying to understand the structures that you see in this that's going to have to tell us the story in what dark energy is doing in particular. The things that are being tackled are dark, and by dark we mean that you just really can't see them. All you can see, if you see anything, is their impact on the things that you can see. And so you can see these galaxies. So on the 1st of July of this year, the European Space Agency rocketed the Euclid telescope on its way out to its orbit around the Earth and Sun at a thing called the Lagrange point 2. I've shown it over here. This is the Sun, this is the Earth, and not at all to scale because this distance is about 90 million miles, and the Lagrange point is only 1 million miles away. And that allows the satellite to track the Earth as it goes all around the Sun. The reason that it has to track is that it's taking data all the time, and it has to be able to send that data back down to Earth. So it can't get too far away from Earth if you're going to see it. Euclid's mission is to explore the composition and evolution of the dark universe. It is to create a great map of the large-scale structure of the universe across space and time by observing and recording billions of galaxies out to 10 billion light years away, over more than about 1/3 of the sky. The data that Euclid records will reveal how the universe has expanded over time and how its structure has evolved over cosmic history. All this should expose a great deal more about the interaction of gravity, the nature of dark energy, and dark matter. When scientists use the word dark, they mean the dark object doesn't emit any light and there is therefore invisible. So how do we know anything about the dark sector? Well, we've known about dark matter for some time, because it's accounted for strange behavior in our own galaxy. The stars in our galaxy are moving much faster than they should be if their motion was only due to the visible stars that you can see in our galaxy. The stars in our galaxy are all tied together by the gravitational attraction of the total mass of the galaxy. That's what holds it together. And think about the following simple situation, if you can follow it. If you consider a light object in a circular orbit around a very heavy object, the thing that makes it go on that circular orbit is a balance between the gravitational attraction that this thing has and the speed that it's moving with. And when they're just perfectly balanced, you're able to make a nice circular orbit. The important thing to know is that that orbit requires that the velocity of the orbit should get smaller as you go further and further away from the mass, from this mass. So what you actually see, however, is when you're looking at the velocity of things here. Here's the velocity in kilometers per second, and this is the distance in light years that you are away from the center of our galaxy. And when you get, this is our galaxy here, our solar system is somewhere in around here, circulating around the center of the galaxy. I think it takes something like 280,000 years, if I remember right. But at any rate, what you find is, oh my gosh, things aren't slowing down at all. They're actually speeding up. So what could be going on? Well, the explanation that one has come up with is that our galaxy, the Milky Way, is actually surrounded by a big glob of dark matter. And that dark matter provides about 90% of the mass, the total mass of our universe. So that what you're seeing when this velocity is being determined is not by the mass of the visible objects in it, but by the dark matter that actually is surrounding it. So we're in a sense immersed in that dark matter, and fortunately, as you can tell, it doesn't interact very strongly because you're totally unaware of it, thank heavens. But it is there, and its impact is totally clear. Except these are rather beautiful astronomical pictures of things that one is able to put together in outer space. Something 3.4 billion light years away is a collision, is imagined to be the collision between two galaxies. The blue light here represents the dark matter associated with these two galaxies, and the red stuff is the normal visible matter, the stuff you can see. So, and it does look like what happened is these galaxies passed right through one another. The normal matter, the kind of stuff we're made of, interacts quite strongly, whereas this blue stuff seems to be totally unaffected. So that's one of the characteristics that dark matter shows, is it seems to have no interaction whatsoever other than gravity. And you wonder, well, wait a minute, how can you see dark matter? You actually don't see the dark matter, but you know it's there by an effect that I would call, that is called gravitational lensing. So there are stars behind these things that when the light from those stars is emitted, it is distorted by the passage of that light through this dark matter, and we'll say a little bit more about it. So if you have a big blob of dark matter sitting between you and the source of something you're looking at, what you you see is you don't see that object where it is. You actually see it because the light from it is bent onto your eye, and you think it's out there or maybe over here. So, and there's another picture of another collision that looks exactly the same. So dark matter, whatever it is very weakly interacting stuff. It doesn't seem to radiate, and, well, we've been totally unsuccessful in figuring out what it is. Now, dark energy was absolutely unknown until about 1990, when astronomers observed a totally unexpected acceleration expansion of the universe rather than the expected deceleration due to gravity. This figure on the right, which is not very helpful, but studied in great care, it shows that the difficulty that they had, they were looking at things that were really a long way off, supernova explosions, that they thought they understood quite well how much light you should expect from it. And these supernovas that they were looking at that were further and that were really a long way out, seemed to have the property that they weren't as bright as you thought they would be, as they should be. And it took quite a while for them to figure out what was going on. And what was, of course, going on was that previous to this time that you had observed them, these things were moving slower than expected, and something all of a sudden interceded to get their velocity now to start, in a sense, accelerating. So scientists now do not know the composition of either dark matter or dark energy, but that stuff makes up 95% of the mass of the universe. The matter that we and anything we can see only accounts for less than 5% of the mass of the universe. It's humbling. We used to think that we were the center of the universe, that things revolved around us. And not only do they not revolve around us, we are really a pretty small and insignificant part of this universe. But I'm getting really way ahead of the story. The story actually begins about 100 years ago. In the late 1920s, the astronomer Fred Hubble noted that there were objects beyond the Milky Way that were, and he noted that those objects, the further away they were, the faster they were moving. So he made a little plot here of the distance of how far away these things were and it's pretty bad data that he had, and he wasn't really quite sure of what he was doing, but his guess that what he was looking at was an expanding universe, because the further away these objects were, the faster they seemed to be moving. If the data was flawed, flawed to the point that when you took this data and figured out, well, when was it all together, it gave you an age of the universe that was just 2 billion years. And one knew, well, that's wrong, because by that time they knew that the Earth was 5 billion years old. So this couldn't possibly be right. And there wasn't really a great deal of attention paid to it. But one thing that happened was the realization that, first of all, they now realized that the whole of the universe isn't the Milky Way. That's what was thought about at the time that Hubble was there. But there were objects out there beyond the Milky Way, and those objects, whatever they were moving away from us, and the further away they were, the faster they were moving. The way that he could tell how far away they were was he thought he understood that Cepheid, a kind of star called the Cepheid variable, and he knew how much light it should be giving off. So by the amount of light that he could see, he thought he could tell how far away it was. Of course, when I say that he could see, I mean that he could see in his telescope. And how could he tell how fast it was going? Well, that was a little easier because he could look at the spectrum of the light that came from these things and see that there was a shift in it. And there's a well-known Doppler shift due to the fact that things were, when they're moving away from you, their wavelength gets longer. And so he could readily tell how fast these things were going, but his guess as to how far away they were was not really very good. Now, as telescopes got better and astronomers learned more, the diagram really greatly improved. So this is the distance in megaparsecs. That's a parsec is a unit that astronomers use. I don't want to try to explain to you where it comes from, but just it's 3.26 light years. Okay, so they're now looking out at things that are millions, because it's millions of parsecs away. This is the original data that Hubble took down here in this corner. You can see his telescopes weren't so good, so he couldn't see very far out. But boy, that picture seemed to last. And if you took a constant for this thing, you would say, gee, that velocity looks like it's somewhere between 100, somewhere between 50 and 100 kilometers per second per megaparsec. And so here's the value that one was getting for that Hubble constant since 1920, starting with Hubble's original bad measurement. Now, in 1964, I had just gone to Princeton at that time, and they were very much involved in this accidental discovery of what is known as the cosmic microwave background. There were a couple of engineers up at Bell Labs that were trying to understand how much noise there was in space. And lo and behold, they found, good God, that it seems that there's some radiation out there that's at a temperature of about 3 degrees, and it's the same in every direction that we look. And they were totally puzzled by this. The physicists in the Princeton physics department were already pretty keyed in to what was going on, and so they were able to explain to him that what these guys were seeing was the first visible light that you could see in the universe. So when the universe begins at the Big Bang, you just get this very hot, expanding gas of electrons and neutrinos and photons, and you can't see a darn thing in them at all. It's like looking at the sun. If you were to look at the sun, you really can't see anything because light inside the sun keeps bouncing around. Light created at the center of the sun takes 1 million years to get out to the surface of the sun, and once it gets there, it only takes 9 minutes to get to the Earth. So it's just an indication of how invisible things were in this thing, and all of a sudden, the universe, which had been expanding and cooling, got to the point at about 3,000 degrees that all of a sudden, the electrons and protons that were there all of a sudden combined and made hydrogen, and that allowed the light to increase in path length by a factor of about 1,000. So all of a sudden, you could see. And the light that these guys were seeing was that light that was released. If you looked out at the universe at the time the light was released, it would have looked to you like a big orange sphere, because that thing was at about 3,000 degrees. But the fact that the universe has increased in size by the factor of somewhat over 1,000 in the 3.8 billion years that it took the light to get to us, just meant that the temperature of that stuff had dropped to something like 3 degrees above absolute zero. So the discovery of that cosmic microwave background in '64 is, to my mind, the most important event in cosmology. Up to that time, most scientists treated cosmology as just a speculative game that people played around in and really shouldn't take it too seriously at all. But all of a sudden, with the realization that you are seeing this cosmic microwave background, and it's really the first visible thing that you can see, and it occurs something like about 400,000 years after the Big Bang. I've just shown it sort of but in a picture over here. Before that, you're just cooling down, and light is just bumping all around, scattering off the electrons, and can't really get out. All of a sudden, the electrons and the protons form hydrogen atoms, and light is now free to escape. So it was a remarkable thing, and it's the earliest thing that we can see in the universe. So people then went after this in a very, very big way, and this thing that Penzias and Wilson just saw as a big orange sphere at a temperature about 3 degrees, became the object of very, very advanced telescopes flown into space. And this is now a picture of the total sky at the time that that microwave, cosmic microwave background was released. So if you put a coordinate system on it, so you go from 0 to 360 degrees, that's like turning around and looking all around at the sky, and then up and down. So this is a total map of the surface of the visible universe at that time, and there were very small variations in it. Yeah, the changes in temperature that one could see were just 3 10,000ths of a degree. So over in this place here, this number could change slightly, and some places appeared to be cooler, but it wasn't really that their temperature was different. What it meant was it was denser right here, and gravity kind of made those photons have a longer wavelength and appear cooler. So this really is kind of a density map of the center of that, of the surface of that object that you were looking at. And what was going on in there was there was a whole bunch of dark matter and a whole lot of light and electrons, and the dark matter would gravitationally attract the other matter to it, and the photons would push against it and push it out. So there were just a whole set of spherical waves coming out at this thing, and they show up finally on the surface of that sphere. And this is a picture of the very fine structure that appears between 70 and 90 degrees. So if we go back, we're now looking, if you remember, I had that scale on here. So this is looking at details on small regions of this surface. And you can just see the exquisite detail that they have of that surface. That surface then could be fitted with a theory that was, in a sense, kind of miraculous. I'll just tell you what it is. The name of it is lambda cold dark matter, and it tells you the relative amounts of dark energy dark energy that we have now, the amount of normal matter, less than 5%, and the amount of dark matter, which was about 25%. And this was such an exquisite fit to this particle granularity that you thought, my God, this is really amazing that such a simple model could end up giving such a great fit to the observation of the cosmic microwave background. So this is a picture of what I was trying to explain to you. So we'll start out at the beginning. So this is the time in millions of years. So it'll start over in a minute. So back in the beginning, there's the dark matter staying in there, the electrons and protons moving on out, neutrinos rushing out, and finally the photons which we're doing all the pushing, finally out here when the matter completes, the photons can escape and off they go into outer space. That's a hard thing to follow, so here it is, slowed down. So this is a picture at 110 years after the Big Bang. Nothing much going on, just hanging in there. Then, as time marches on, 14,000 years after, you now start, the neutrinos are starting to run out. The reason neutrinos run out is they don't interact with anything, so they just take off and they're very light and run away. And these are the photons are pushing the electrons and protons out. This is after 230,000 years. We're getting now 380,000 years, getting near, and the photons now are just getting ready to all of a sudden escape. And they run off, and now you're left with just normal matter here in blue and dark matter here in black. And the only thing that's so all you can do is get out there, take a great map of the sky, and try to fit as best you can it for these circular distributions of matter that might tell you what the size of the baryon acoustic oscillations are. So this is the data that Euclid is going to take. Euclid is going to measure basically the stars that are from about 6,000 light years away to those that are 10,000 light years away, and map this whole thing for about I think it's over a third of the sky. So when they're done, they will have a map that has 1.5 billion galaxies in it. What I had shown you before, the stuff from the Sloan Digital Sky Search, was just 1 million galaxies. So this is an enormous undertaking that these folks are involved in. So what are they going to try to measure? They're going to be looking for this correlation between distributions that will reveal to them the size of the baryon acoustic oscillation as a function of time. And this is an artist's impression of the way it should go in a perfect world. The other thing they'll be measuring is weak lensing. I didn't say much about that, but that's the way they're going to be able to talk about finding the effects of clumping of dark matter. So what would happen is if you had, here's a picture of, you had a bunch of unlensed sources. If there's some dark matter in between you and those sources of light, they get distorted. They get bent as they go around that dark matter, and by that lensing effect, you can tell where the dark matter is located. So here's a picture of some of the things that you see. One of the things you see is an Einstein ring, and the other thing that you pick up from now and then, they're called Einstein crosses, where you actually pick up individual images of the stars behind the clump of black matter. So here's what the Euclid telescope looks like. It's kind of a modest looking little package. as you might imagine, it's got its back to the sun and peers out into outer space. The way it works optically now is there's this big mirror here. It's about 1 meter in size. The light comes in, is reflected off and focused onto a secondary mirror that then in turn focuses the light onto basically a light collecting camera of very great power and resolution. So here's Euclid's journey out to L2. Here it was being launched. It was originally going to be launched by the Russians, but since it was in this July and Russia had invaded the Ukraine, they decided, the European Space Agency used Elon Musk to actually end up launching this thing. And here it is running around now in its orbit out at L2. This is, I think, a wonderful picture for you to keep in your mind as to how it looks. Here's the sun shining on the Earth. That's probably the moon in orbit around here. And here, about 3 times further away, is the Euclid telescope getting a lot of solar energy that it can use to keep sending the information back to planet Earth, and also keeping the temperature down so that good pictures can be taken. This is the antenna that gets the information from Euclid. So Euclid, for about 4 hours a day, pours down an incredible volume of data that gets stored in places in the US, Europe. I don't think China or Russia is involved at all.
Where is that?
This is the plots of the pieces of the Earth that, or the sky that Euclid is looking at. These portions that you see looking like this, you don't look in this direction at all because that would take you looking directly into the Milky Way, and you can't really see very well there. So this is the stuff that you are actually mapping. This was an early commissioning test. Took about a month after the thing got into orbit, and they were very happy with the image that was coming back. It looked like the device was working beautifully. Here it is in somewhat more detail. And as I said, it'll be out there for 6 years taking this data and broadcasting it back to Earth. But some problems showed up. On the 1st of August, it turned out there was some sunlight creeping into the pictures. I don't have a good picture of that, but that was easily fixed by just tilting the Euclid in just a better way so the sunlight didn't get in. Then on the 27th of September, all of a sudden, the guidance system seemed to be off. And this is what happens. That's really pretty serious. Here's a star, and all of a sudden the guidance system starts to wander. And here you, rather than seeing a star at a simple location, it starts to wander all over the place. So it would be a great mess. And it was discovered that this only happened in places where there wasn't a great deal of starlight for the thing to remain fixed, and it was being misled by cosmic ray collisions that created ionization and light, and threw the guidance system off. They had that fixed, and by October 6th, everything is fixed, and everything seems to be fine and working as it should. So I'm sorry not to be able to present any results to you today, as I was just describing the mission ahead for the newly launched Euclid telescope. With Euclid and the Webb telescope out there at L2, we should learn a great deal. It's daunting to think of the task that Euclid set for itself, looking for imprints of the invisible features of our universe, dark matter and dark energy. While there's clear evidence for their effects on the visible universe, we have no idea of what either of those things are. We still could be in that state when those two space telescopes have completed their mission, but I expect that the inconsistency in the Hubble constant will end up being resolved by their findings. Thank you for your attention.
They have lights on?
Jerry, that was really an impressive job of summarizing stuff. I have very, very minimal hard science background, but I was following that and I'm just blown away. Could someone turn the lights back on, and then I'm going to, let's see, I think, I'll go with you, and then...
Jerry, this must be a very expensive case to send Euclid on its way, and how much is that, and who's paying for it?
Okay, so as I said, it's the European Space Agency. The cost that they're putting on the mission itself is about $500 million. I think if you integrate over the amount of time it's going to take to analyze the data and the number of people that have to be involved in that analysis, the cost will end up being well over $1 billion.
Who's paying?
Mostly Europe. We pay scientists who work on it, but they're happy to be working on that. They find it, to be one of the most exciting things they could be working on. So I would imagine that probably NASA is spending something like $300 million a year paying the scientific people who would be working on this. But they're mostly at universities, and I guess NASA is involved largely through the, oh dear, what is it? The Rad Lab out at Caltech.
Yeah. Henry next.
Two things. Attempts to detect dark matter have been based on the idea that it does interact in the weak interaction. Is there any further idea of whether that's so or not?
No. There's no evidence, Henry, that it interacts any way other than gravitationally.
Is there evidence that it doesn't interact through the weak interaction? Because some people think it does.
Oh, you bet. Well, if it did, you have a chance of detecting it.
Yeah.
So that's one reason that they might advocate that it would interact that strongly. But there's no evidence that that's true. Because if it interacts only gravitationally, there's no way that we're going to be able to figure out what the devil it is.
When was it launched again? July 1st? The question, when was it launched?
When was it launched? July 1.
Yeah, it was last July 1. Okay.
If there's a conflict between the observable data
Yes.
and the model.
Yes.
Is there any reason we should assume that it's a deficiency in the data and not a deficiency in the model? And is there...
Very good question.
Yeah.
As you might imagine, as that dilemma has grown over time, I would say it's been going on now for about 6 or 7 years. They have just poured over everything they can think of and can't seem to find any inconsistency in the data. So it really seems to be tied into very much the way the measurement is done. And both groups are quite confident of their measurement and their numbers and their analysis. But the fact that they don't agree, and you have to take the value that people are observing now is the right value. So you have to figure out, why is the model giving the wrong value? And that model is so, in a sense, bare bones. Its only pieces are dark energy, dark matter, normal matter, and that's it. And they think they understand how those things should evolve in time, and having understood that, you should know how to predict the Hubble constant as a function of time.
Is there as much effort being put into re-examining the model as there is effort, technological effort, being put into improving the observations?
Let's see. I don't quite know how to answer that, because I'm not sure I understood it. Want to try me again?
Yeah, I'm not sure I know how to ask it. If there's a conflict between the model and the current level of
So it's the
observation.
model, and the model it uses as its data what you see in the cosmic microwave background. So that's a measurement from something that came out 13.8 billion years ago. And so that's that observation. And now you're comparing it to a measurement that you're making now from things that are nearby. You could call them now, and they differ. And the thing that ties the cosmic microwave background value to what you should be seeing now seems to be things that are well understood. So there are some people who believe there's a problem with general relativity, there's something quite revolutionary going on that we don't understand. So there's a whole host of possible things, but nothing at all compelling.
Judy is next.
You showed a picture of the antenna. Where is it located?
Yeah, I wanted that.
Gee, that's a good question. I'm not sure.
Looked like the middle of probably the U.S.
There.
Yeah, there.
Yeah. You know, I can't help it. But I would agree with you. It looks like New Mexico or something like that.
They don't want people to know. They don't want to...
recognize it's a raid.
Yeah. Okay.
That's some antenna.
In one of your early images, you showed the collision of two galaxies,
Yeah.
and the visible matter seemed to be merging, the blue dark matter seemed to be staying outside. Any explanation for that?
Yeah. What one thinks is the dark matter just because its only interactions are gravitational, it just pass through. And whereas the normal matter, like ourselves, has largely electromagnetic interactions, and those are much stronger. And so that's what causes them in collisions to end up lighting up, and they become actually readily visible. But that dark matter, it really is dark matter. So I would just like to say, I'm sure you're going to grow sick and tired of me. I'm going to be up on Monday with Don McMillan over there doing the play, and then on the following Monday getting started on artificial intelligence.
We'll get sick and tired of you on a scale of light years.